now we're continuing our lecture on these things. Anyway, don't need to reintroduce it every 10 minutes. So Dr. Charbon explained to us that there's these two different forces, and we started to talk about this Archimedes force, which is the same thing as buoyancy. And you are all most familiar with buoyancy and understanding how it works. If you think of a boat, here's a boat, and the boat is floating on the ocean, and it floats because it displaces a certain amount of water. And if you analyze the bottom of the boat here, this area that's underwater, the force of buoyancy is going to equal the volume which has been displaced times the mass of the water that would fill that volume. Yeah, it's it's basically mass. Anyway, you can just look at it this way. This is maybe a simpler way to write it. Basically, the force of the buoyancy is the same as the weight of the same volume of the water that's displaced. So this is the famous story of how Archimedes determines that the king asks Archimedes, do you guys know the story? The king asks Archimedes to determine if the crown is made of gold or is it fake, and he can't figure it out for a long time, and then he gets in the bathtub and he sees the water get displaced, and he says, Eureka, because that's his wife's name. I've got it, right? Oh. Eureka was Archimedes' wife. Oh. Eureka, I got it. Because what he got was this idea of density, that gold is denser, meaning a cubic foot of gold is going to weigh a lot more than a cubic foot of, say, silver or iron or some other metal. Okay, so that's what he realized. And so anyway, this force of buoyancy is named after Archimedes. It's the Archimedes force. So in water, if you submerge, let's say instead of a boat now, because a boat will sink if you submerge it, usually, because the top is open. Let's say you've got a submarine, right? And it's floating on the surface of the water. It's Red October right here. Okay? There's Red October. It's floating on the surface of the water. Yeah. And so the Archimedes force is holding it up. Then let's say, I don't know, let's say it somehow gets attached to a huge lead weight and it pulls it down, and so now Red October is right here. The force pulling Red October up is going to equal its entire volume in water. That's the amount of force that's going to be pushing it up. So you all understand if you push a balloon or an empty barrel underwater, it's going to want to come up with a great deal of force. You've all experienced that. Well, now watch this. You don't have to be in water to have the Archimedes force act on you. You can have buoyancy. You can have buoyancy even in the air. Okay? So here's a balloon now. We're back to our balloon example. Here's our balloon, and it's floating in the air, and there is a force on the balloon up equivalent to the mass of the balloon or the volume of the balloon in air. Meaning, if you had a volume of air the same as the volume of the balloon, that air has some weight to it. And that amount of weight is now pushing up on that balloon.
So the bigger the balloon you have, essentially the higher it will go?
The more the Archimedes force will act on it. Now, well, here's the thing. If the balloon is filled with air, you neutralize the Archimedes force. Good, you were going to ask, sorry, Thea.
That was my question. I wondered if the mass you're counting is just the shell around the air that's inside.
No, you got to count the air inside. So if it's filled with air, the Archimedes force is very small. It's just the volume of the rubber itself, which is extremely small. But if it's filled with helium, then or if you could build some kind of super strong, super thin shell with a vacuum inside, I don't know. This isn't working. Okay, we have slight technical problem here. Sorry, class. Okay, we fixed it. If the balloon was filled with helium, there would be a larger Archimedes force on it. But the Archimedes force acts in the air as well, and it affects very light objects, okay? So, but essentially, the main force that affects falling objects in air is going to be the force of air resistance. So, getting back to the whole beginning of the conversation, Aristotle was right in that from the very crudest observation, lighter things do fall faster. Slower. Right, correct. However, just taking the experiment a little bit further, you can show that objects of very greatly different masses will fall at basically the same speed, even in air. So this brings us to Galileo. And actually, before we get to that, some of you had some questions. What were the questions? You had a question.
I have another question. It's about the feather. The feather
Yeah.
has a lot of air, not much surface.
Okay.
Is that the same as the balloon? Or, I mean, it's spread out,
Mm-hmm.
but it's usually...
Yeah, the aerodynamics plays a huge role in the speed of a falling object. So, for example, here's a ball. Here is a missile pointing down. And here's a feather. The force due to drag, which is what we call air resistance. Another word for air resistance is drag. So drag, these terms are interchangeable. Air resistance. So FD, or the force of drag, is proportional to the cross-sectional area of an object. So if you take a cross-section of the ball, obviously you end up with a circle that big with A equals pi r squared. Okay? So the air resistance is essentially going to be, for the air resistance on the ball, so or drag on the ball, so force of drag on the ball is going to equal pi r squared times its velocity times some constant c. And I don't know what the value of that's going to be, but it's going to be different for different fluids. So there'll be a different constant for air, for water. Okay, and so obviously the one for water is going to be a lot higher because the force of drag is much higher in water. Yes, Andre.
So the cross-sectional area, that's the one parallel to the ground, right?
Yes, in the direction of motion. Yeah. Now, the other thing you can do, like let's say we slice the rocket in half, it's still a circle, but it's much smaller. Okay? And because area is proportional to radius squared, the smaller that cross-section, your force of drag goes down exponentially. This is the beauty of mathematics and physics. You can look at these equations once you start to know the language a little bit and see what they're saying to you. This is saying that you make the ball with half the radius, it's going to be, it'll fall, you'll cut the force of drag by 4. That's what this equation is telling us. Now look at the feather. It's basically all cross-section. The whole thing is cross-section. So the ratio of mass to area is, or mass to cross-section, there's much, much more cross-section than mass here. Okay, so if we want to look at that ratio, anyway, there's much, I don't want to get into it too much, but no, it's a great question. We got to answer it. There's much more area than mass on the feather. There's much less area than mass on the rocket, and there's some other relationship for the ball, which we could determine very carefully, but we don't want to take the time right now. So basically you get the idea that the aerodynamics is going to affect the force of drag, and the more the force of drag, the faster or the slower the thing's going to fall. Okay? Now, okay, so that's that question. Any other questions? Other questions? Nicholas? 10? Okay, we'll go to the next lecture.